Here we have a problem where we've got to use calculus. We can't use our rules for volume to find the volume of a cone that has a height of 12 centimetres, and we're given the property that its radius is always half its height. So probably a good idea to draw yourself a quick little diagram of a cone. Okay, so it has a height of 12 centimetres. So it's got a radius of r. If we were to take out a very, very, very thin slither, and we were to blow it up, expand it, magnify it. So if this is h is a variable. So if it was very, very thin, we could say that the height of this slither is dh. So from there to there is dh. If it was very, very thin, it would be very much like a cylinder. So actually we might call that capital R, and we'll call this one here little r. So from there out to there is little r. So this has got a radius of little r. So if this is dh, so it's a very, very thin slice you've taken outside the cone, the volume of this, which we'll denote by dv, is going to be approximately equal to, now this is very much like a cylinder, and it's the area of the base times the height. Now the area of the base is a circle, so it'll be pi r squared, and the height is equal to dh. So the volume of this little slither that we've actually cut out of here of height dh is approximately equal to pi r squared, the area of the base, the circular base, times the height, because this is very much like a cylinder. Alright, now to get the total volume, it'll be just the integral of the volume of dv. So the integral of this with respect to h. So that'll be equal to the integral of pi r squared dh, and we want h values from 0, because it has a height of 12, from 0 to 12. Now at the moment we've got two variables here. Pi is a constant, that's okay. We're going to find the integral with respect to h. But r is going to change. As this little slither here moves up and down the cone there, r is going to change. So in order to be able to do this integral, we need to be able to get this all in terms of h. If we go back to the question, we've got another bit of information up here. The radius is always half its height. So that bit of information says that r is equal to a half of h. So, or h on 2. So instead of r now, we can say it's the integral between 0 and 12 of pi. Instead of r, we can write h on 2. Now it's all squared, dh. We've now got all of that in terms of one unknown, which is h, which is finding the integral with respect to h, so all should be good. So pi as a constant can come out the front. The integral of h squared on 4, so the 4 can come on outside as well, because when we square that we get h squared on 4, so there'll be integral of h squared dh between 0 and 12, and the integral of h squared, add a power on that power, between 0 and 12, equal to pi on 4. Now 12 cubed minus 0 on 3. that's just going to be equal to 0, so that's pi on 4 times 12 times 12 times 12 over 3. Cubed, 12 times 12 times 12, 3 4s are 12. I'll cancel with one of those 12s. 12 times 12, 144, so 144 pi centimetres cubed. Alright, so 144 pi cubic centimetres. So the concept here with integration is an adding up. And we know that if we take a slither, that slither would have a volume of approximately equal to pi r squared dh, if dh is the height. dh is a small increment of h, and that's a corresponding small increment in the volume. So by adding up between 0 and 12, all these slithers, we're going to get the total volume of the cone. And the next step involved making the substitution, finding enough information in the question to be able to do a substitution, so that because r is a variable, we don't want a variable there and then finding the derivative with respect to another variable. So we've got r's and h's, both of them variables, so we can't have that. So we actually have a link between the two, and that allows us to do the substitution, take any constants out the front, and then do the final calculation.